Let's say you got 100 euros and you go to your bank and deposit that money. And your bank says, for that we can offer you an annual interest rate of 10%. And then you realize that this is either a dream or a math video, because that interest rate is insane. But let us follow through with this example, and sure enough, after a year, your bank will pay you 10% of your 100 euros, so you now have got 110 euros in your account. Let us generalize this a bit. Let's say you started with a principal sum of P euros, and the annual interest rate is R. So in our example, P was 100 and R was 10%, that's 0.1. And after a year, we ended up with A equals P times 1 plus R euros. So in our case, there was 110. This is if the interest is paid out once per year. Now, my bank, for example, pays out interest 4 times a year. And in general, the number of interest payments in a certain period of time, usually within a year, is called the compounding frequency. Let us now study the effect of compounding frequency on this result. We could, for instance, consider 2 payments per year. So after 6 months, after half a year, we have A equals P times 1 plus R over 2. Because R is still the interest rate for waiting 1 whole year, but we only waited half a year, so we're only getting half the interest rate. So in our example, that means after half a year, we would have 105 euros. Now, after 12 months, we get the amount of money that we have after 6 months, so that P times 1 plus R over 2, and then we collect an additional interest of R over 2, so we multiply by 1 plus R over 2. So after a whole year, we would end up with 110.25 euros, so 110 euros and 25 cents, which is more than we got when interest was paid out only once per year. And the reason for that is that in the second half of the year, we were also collecting interest for these additional 5 euros that we made in the first half of the year. And also in the following year, we will collect interest for additional 10 euros and 25 cents that we made this year. This is the concept of compound interest, which Albert Einstein supposedly called the 8th wonder of the world. But let us focus again on compounding frequency and generalize this to n times per year. So after a year, we would end up with A equals P times 1 plus R over n, and this gets paid out a total number of n times, so we can just put this to the nth power. And now an interesting question is, what happens if we completely overdo this and compute the limit of n going to infinity of P times 1 plus R over n to the nth power? So we're going to pay out interest an infinite number of times within a year, but it's also an infinitesimally small amount of R over n each time. If you know the exponential function, you already know the result of this computation, because this is exactly P times e to the R. And in our case, that gives approximately 110.51 euros, rounded down. But isn't it strange that the exponential function suddenly appeared out of nowhere in this simple thought experiment about interest rates? Let me illustrate this once more by putting P equal to 1 and R equal to 1. So we're now considering an interest rate of 100% and we start with 1 euro. So with a compounding frequency of 1 payout per year, we would simply double that investment from 1 euro to 2 euros. And now we ask ourselves, how much better can we do by increasing the compounding frequency? So what we compute is the limit of n going to infinity of 1 plus 1 over n to the nth power. And this is 2.718281828 8, 4, 5, 9, yeah. This number goes on forever because it's nothing but E, Euler's number. So if your interest rate of 100% per year gets paid out not only once or twice per year, but an infinite number of times per year, you could multiply your initial investment by a factor of approximately 2.7 after a year. But the thing is, it's not exactly 2.7. The limit of this computation is not some nice number. It's this irrational, infinitely long number that goes on forever, and that seems so completely arbitrary, yet so important in mathematics and the laws of nature, showing just how strange and wonderful math can be.